Right. Who is the next candidate? That's Amy. Then she's in the waiting room.
Perfect.
We let her in.
I'm ready when you are. Thank you, Ursula.
Great. Amy? Hi.
Morning.
Good morning.
Good
Nice
morning.
to meet you.
Hello.
Hi.
Right. So this, I expect, is your first interview. I'll just explain very briefly what will happen. It's just about maths. We're not going to ask
Yep.
about anything else aside from maths. It'll take about 25 minutes. And are you able to write on the whiteboard? We'll share a whiteboard so you can.
I should be able to, but we'll see.
Great. Don't worry if something goes wrong with the technicalities, because if we lose time with that, we'll be able to make up the time afterwards. And even if it crashes altogether, we'll be able to reschedule the interview. Okay, so my name is Ursula. I'm a director of studies here, and James is a director of studies in maths, obviously, at another college. I think then we'll start first with a question from James. Here we go. I'll share the whiteboard.
Thank you. So I wonder, Amy, if you could just double check that you're able to write on the whiteboard here, just to check everything's working smoothly.
Yep, all good.
Perfect. That seems to be good. Thank you. Could we have a new page, please, Ursula? So, which is larger as n tends to infinity? 2 to the 2 to the 2 to the n, or 100 to the 100 to the n? And can you see the question at the top there?
Yes, I can, thank you.
Great.
So I'd look at this by saying, well, we know that, annotate. Sorry about the line.
That's okay.
So as n tends to infinity, so we're going to be looking at graphs here. We know 100 is equal to 2 times 5, 2 times 2 times 2 times 5 times 5. So we know that 100 is equal to 2 squared times 5 squared. And therefore 100 to the 100 to the n is 2 squared times 5 to the 5 to the power of 2 squared times 5 to the, not 5 to the 5, sorry, 5 squared.
Thank you.
That's all to the n. So we've got here in it 2 squared, 2, this which equals, we've got in it 2 squared times 2 squared to the power of n as well. So as n tends to infinity, I'm going to say that 100 to the power of 100 to the power of n is bigger because it contains in it 2 to the 2 to the 2 to the n, as well as other things as well.
So I wonder if you could just double check. Say I'll just write something here. If we have this bracket, if we have something like 2 squared to the n, what happens when we simplify this bracket?
We get, sorry, the mouse, there we go. We get here 4 to the n. I don't know why that's duplicated that.
That's okay. So here we don't actually, this is not equal to 2 to the 2 to the
Yeah.
n.
Yes, oh, of course, because you times it together, yeah.
So I wonder if that maybe changes your answer at all.
So that would be 2 to the 2n.
And now maybe
So
do you have an intuition for which you think is bigger?
Well, 100 to the n grows bigger than 2 to the n. However, 2 to the power of 2 to the power of n as n grows bigger, I'd say that 2 to the 2 to the n grows bigger than 100 to the n.
That's
Because
correct. So Ursula, could we have a new page? And now we believe that 2 to the 2 to the 2 to the n should be bigger than 100 to the 100 to the n. So I wonder, now we have this intuition. You've thought about factoring the base, but it's somehow challenging to compare different bases. I wonder if you can think of any tools you might use to compare these kind of exponential quantities.
we could use logarithms, so we could do log base 2. So because we know that log scale in the same factor as not it, so we know that if, say, we know that 2 is smaller than 100, we know that log base 2 to the 2 will be smaller than log base 2 to the 100. So therefore, if we go log base 2, we're going to have 2 to the 2 to the n is less than log base 2 of 100 to the 100. And we know in logs that, for example, log 6 is the same as log 2 plus log 3. So this one, because it's 2 times 2 times 2 times 5 times 5, that's going to be equal to 100 to the n times 2 plus log 2 of 5, log 25 to the 100 to the n. Yes, that should be right. Yeah. Bringing down the factors.
I'll just to give you a little hint, that will actually, we don't need quite as much information as this. So I wonder, could you try simplifying this expression here? And there's no need to factor the 100s. I wonder if you could try using your laws of logarithms and we can see what happens here.
Well, you can immediately bring the 100 to the n out to the front using the power law of logarithms. And then log base 2 to the 100. We know that is equal to, we can then say that that's equal to 2 plus.
Perfect. So this is just some number and it's going to be a little bit, well, it's going to be bigger than 2. So
Yes.
Could we just have one new page, Ursula, and I'll just summarize where we've got to. So we applied log to base 2, and now we're trying to compare. We're trying to compare 2 to the 2 to the n versus 100 to the n times, let's call it c, where c is this number log to base 2 of 100, which we know is bigger than 2. So it's some positive constant bigger than 1. That should be all we need. So I wonder, could you compare these quantities and see if you can finish off the proof from here?
Because we know this is greater than 2, we can say that 100 n times c is greater than 100 n times 2. So we just need to show that 100 to the power of n is either going to be less than or equal to, it's either going to be less than or greater than 2 to the 2n minus 1. If we then take log base 2 again, we get that n log 2 of 100 is going to be something of 2 to the power of n minus 1. We know this number is greater than 2. Again, so we can just say that this is if we say that that is, so we know that this is going to be greater than 2n, and this is 2 to the power of n minus 1. Oh, we can't do that, hang on a minute, because we want to prove that this is less than. So we can just.
So the inequality is not the right way around. So if I told you log to the base 2 of 100 is less than 7, just to save ourselves working out the numbers. Could you use that to help you?
Yeah, so we can say that this is less than 7n, which is, I've just put 8 there because we know that 8 is 2 to the power of 3. But also we know that powers grow greater than linear factors. So if we know that as n tends to infinity, 7n will be less than 2 to the n minus 1.
Good. So I wonder if I could just ask you 2 more questions just as we
Yeah,
piece
of
it.
course.
So the first is, so you've said quite correctly that 2 to the n minus 1 is going to be larger than 8n as n gets big. I wonder, you don't need to actually do any of it, but I wonder if you could indicate how you might go about proving something like that for all n.
Yeah. So you could draw the graph of 2n minus 1 minus 7n and work out where it intersects 0 and show that as n tends to infinity, that graph will always be positive, which shows that 2n minus 1 must be greater than 7n.
And how might you
That
put
might.
it? This graph is always positive.
You could do it by finding the roots by using the derivative. So there's only 1 or 2 roots, work out what they are, and then show that for one number greater than the larger root it's positive, because we know it won't intersect the y-axis, x-axis again. We know that if one of them is positive, then all of them greater than that root must be positive.
That's good. So we could use derivatives to somehow prove this.
Yeah.
And then just one final thing. So a couple of times in the proof we took logs. So at the end we've argued that this thing is true. I wonder if you could just very briefly explain why that implies the original result we're trying to prove.
Yeah, of course. So if we know that that is 7n is less than 2 to the n minus 1, we know that 7n is greater than n log 2 of 100. Then when we can take powers, because logs and powers scale the same. So if log of something is less than log of another thing, then the first thing will be less than the original thing.
Great. So
we
how
can
might you, could you give a kind of technical word which describes the behavior of log, which means that it respects inequalities?
It scales proportionately.
Right, good. So log preserves inequalities in that sense.
Yeah.
Okay, thank you very much.
That's okay.
Ursula, I think, do we have time? Would you like to ask a question now?
Okay, for a different sort of question now, I'll ask you some graph sketching, and actually in some ways connected to what you've just done. The first thing I want you to sketch is the function y equals learn x. I expect you've probably seen that in school.
Yep. So we know it doesn't exist beyond x negative. So we can ignore this section of the graph. It cuts the x-axis when x equals 1, because the natural log of 1 is 0. As it tends to 0, it gets off to infinity. And then as it curves like that, because if we look at dy over dx, we get 1 over x. So as x gets bigger, the gradient gets smaller. So it gets shallower.
Yeah, that's great. And as x tends to infinity, ln x tends to
infinity as well, positive infinity as well.
Yeah, because why does it?
Oh, yeah. So it tends to infinity as x tends to infinity. Because, or what we're saying is that it's the natural log of e. So we're saying is x equals e to the power of y. So as x tends to infinity,
Yeah,
the gradient's always positive. So the line will never start tending. It will never do that. It will never tend downwards again.
Thank you. Now I'll use a new
Yeah.
and an even easier function if I have y equals a, where a is some constant x? What is this function?
Okay, so there's a couple of cases. So if a is 0, then y will always be 0. So that's the case if a equals 0. If a is negative, so if a is less than 0, then it will always pass through 0, 0.
Mm-hmm.
So this is if a is less than 0. And if a is greater than 0, it's going to look like that. So as a tends to positive infinity, the line will get steeper.
Okay, great. Now, focusing on these two functions, if we put them together, can you tell them whether there may be any intersections? How many, in what cases, and so on?
Do you mean with y equals the natural log of
Yeah,
x?
y equals ln x and y equals ax.
Yeah, okay. So I'm just going to draw the natural log of x. So that's one there. There's 1. So if we're using a equals 0, then there'll only be one possible value.
Mm-hmm.
If we look here, like just as a sketch, imagine that pass through 0. If the line's steep enough, then it's possible that it won't hit at all.
Mm-hmm.
If it hits at a tangent point, so if we get point, so if we have the dy over dx, which is 1 over x, if at a certain point that is equal, that would be the gradient. If the tangent line passes through 0, 0, then that will be, then y equals ax will be the tangent point there, and there'll only be 1 point. But if it's shallow enough here, then it will potentially pass through 2 points. Sorry, that's a terrible line.
The picture doesn't matter. We're not after art here, after maths.
Yep.
So
And
Yep.
So there's a potential it will go through a maximum of 2 points. If it's negative, then it will only ever go through 1, but it will always go through 1 if it's negative.
Yes, that's correct. And can we find out where the point where we have just one intersection?
Yeah. So we're going to have a point. Actually, let's use C rather than X. So this is.
Want to use a new whiteboard to.
Yes, that'd be helpful. Thank you.
Right. Okay.
So we're going to say that it meets perfectly here. Oh, imagine they've met there.
Yeah.
At this one point, and at this point, the gradient. So we've got y equals ax. So a is equal to 1 over x at this point. So I'm going to call this point x naught.
Mm-hmm.
So it's going to be x naught and the natural log of x naught. So we're going to have that at x naught. So we're saying 1 over x naught equals a.
Mm-hmm.
Yeah. Yes, because the gradient. So we're also saying.
That's correct. The gradient has to be the same.
And we're also saying at this point that the natural log of x naught equals a of x naught using the fact that it's this line. I'm really sorry about my writing.
That's okay.
So now we can put in together the natural log of x naught must equal, we know that a equals 1 over x naught. So we've got 1 over x naught times x naught, which is just 1. So then take in the powers. So we're saying x naught equals e, because e to the power of 1 is e. So the point is going to be e, now what it's going to be e and 1. So we're saying there that a is equal to 1 over e. So when y equals 1 over e, the line y equals 1 over e times x will hit this curve, hit natural log of x just at exactly 1 point.
That's correct. So you found the point and what the slope of the straight line should be. That's great. Would the question have been more difficult if we were to find the intersections of a different curve with the learn x, like for example, y equals x squared, or ax squared, or ax squared plus b. I don't want to go through the whole thing, but just to tell me, so for you to tell me your strategy.
Yep, so I think, yes, it would be more difficult. So if it was y equals ax squared, then we'd have here, it would be a squared there, it would be a squared there. And we'd be saying that this would be, we'd end up with squares everywhere. However, actually, this point would cancel out. So it'd still be the natural log of x naught equals 1. Okay, so that would probably actually be the same. If we had a different, let's see, so there was a y-intercept that wasn't 0 for the line, then I think it would be more difficult to work out because we'd have to introduce in this one to work out what a is.
Quite rightly, when you were looking at the intersections between the straight line and learn x, said the tangent at that point has to be the same.
Yep.
So if our function is not y equals ax, but y equals ax squared, does anything change when we compare?
Yep, so we need the tangent of x squared, ax squared to be the same as the natural log of x. So the derivative of x squared is not just going to be a, it's going to be 2ax instead.
Yes, yes, of course. But otherwise, the strategy is the same.
Yes.
Okay, I think we've run out of time now. So if you have any other questions, maybe you can ask, although you don't have to have any questions at all. And this can be just the end of your interview. Thank you.
Awesome. Thank you so much.
Thank you for coming. Nice to meet you.
Bye-bye. Take care.
Bye-bye.
Bye.